We defined uniform continuity and explored some very elementary consequences of that definition, namely that continuous functions on closed intervals are also uniformly continuous. So in this video, we are going to explore a couple more results regarding uniform continuity. Okay, so the first is the following. Okay, so what this result tells us is that if you have a function f which is uniformly continuous on some set S, there's no restriction on S. Okay, and if you have Sn which is a Cauchy sequence in S, in other words, it takes values in S and it is Cauchy. In that case, f of Sn is also guaranteed to be Cauchy. Okay, so if you have uniform continuity on S, then if you construct a Cauchy sequence within S, the corresponding sequence of function values is also guaranteed to be Cauchy. Okay, so that's the statement. Let's go through the argument and then we'll see a couple of places where this can in fact be applied as well. Okay, so the proof is actually remarkably straightforward. You just have to apply the definition of uniform continuity and the Cauchiness of Sn. Okay, what does uniform continuity of f mean? That given any epsilon greater than 0, there exists a delta such that for all x and y in S which are at most delta apart, the function value is at most epsilon apart. Okay. Additionally, we know that the sequence Sn is Cauchy. So the fact that Sn is Cauchy implies that since Sn is Cauchy, there exists some n naught such that any elements of the sequence are at most delta apart for all m and n greater than or equal to n naught. Okay, so all of this, you assume that some fixed epsilon is given to you. The uniform continuity tells you that there exists a delta such that so long as x and y are within delta distance of one another, f of x and f of y are at most epsilon distance from one another. Then you say that for that particular delta that you got, the Cauchiness of Sn implies that beyond a certain point, let's call it n naught, any two elements of this Sn sequence are at most delta apart. Now all we have to do is patch these two together, implying that for all m and n greater than or equal to n naught, since Sn and Sm are at most delta apart, it follows that f of Sn minus f of Sm is at most epsilon. And that completes the argument, because that's exactly what it means to say that the f of Sn sequence is Cauchy. Given an epsilon, you should be able to give me a certain threshold, in this case it's called n naught, such that any two elements of the sequence beyond n naught are at most delta apart. And you are able to show this by arguing that beyond this n naught, any two elements of the Sn sequence are at most delta apart. Right? And that in turn follows from the Cauchiness of Sn. So yeah, that's it. The statement is fairly straightforward. If f is uniform, the result is fairly easy to prove. If f is uniformly continuous, a Cauchy sequence in the set S will result in a Cauchy sequence of function values. Okay. Now let us apply this result. Now recall that we have already said that this function f of x is equal to 1 by x square is not uniformly continuous on the open interval 0, 1. Okay, is not uniformly continuous on the interval 0, 1. What we will do is we were we already gave a direct argument for this, a first principles argument for this. It turns out you will be able to arrive at the same conclusion by apply this theorem. So we will see how the same conclusion can be obtained using the above theorem. Right? It gives you a more elementary argument for why this function is in fact not uniformly continuous. Right? How would the argument go? The argument would go as follows. So suppose that this function is in fact uniformly continuous on 0, 1. So assume, for getting a contradiction, f is uniformly continuous okay, and now construct the following sequence. Sn is equal to 1 by n. Yeah. Now this sequence is clearly Cauchy. Okay, which implies from the previous theorem that f of Sn, f of xn, which in this case would be n square, is Cauchy. But we know that the sequence n square is in fact not Cauchy, right? It's in fact a divergent sequence, and so that is your contradiction. Which implies that our assumption that f is uniformly continuous on 0, 1 is in fact not true. Okay, so that was the first of our results. Now we will have one more result which also gives us a condition for checking uniform continuity over open intervals. Okay, and that the basis of that result is the following definition. So we say a function f tilde is an extension of some function f if the following is true. Firstly, you want that the domain of this function should be a superset of the domain of f, and these two functions should agree over the domain of f. Right? So f tilde is going to be an extension of f if its domain is a superset of f, but within the domain of f it agrees with f. Right? So that's a natural reason to call f tilde an extension of f, because it agrees with f over its domain but extends that domain. So therefore it's the extension. Okay. So if you are comfortable with this definition, now I can state the main result with respect to in relation to uniform continuity. So a function on some open interval of the form AB is uniformly continuous on AB if and only if it can be extended to a continuous function, let's say f tilde, on the corresponding closed interval AB. Okay, so this tells you something very nice about when you can expect uniform continuity to hold over open intervals. And it tells you that uniform continuity can hold for a function over some open interval if and only if there in fact exists an extension of the function which is continuous on the corresponding closed interval, right? And this is if and only if. So uniform continuity on open intervals requires that there be a clean extension of this function which is in fact continuous on the corresponding closed interval, such that the boundary points are also included, right? Then and only then can a function be uniformly continuous on an open interval AB. Okay, now let's go through the proof for this. Okay, now one side of this is fairly straightforward, which is that if there is an extension to a continuous function f tilde on the closed interval AB, the original function f, I think I should have called it f. The original function f is in fact uniformly continuous on the open interval. That's easy. So one side is easy. That is, if there exists extension f tilde that is continuous on AB, then I claim that f is in fact uniformly continuous on the open interval AB. Well, why is this? We know that f tilde is uniformly continuous this we know, right? Because continuous functions on closed intervals are uniformly continuous, which in turn implies that f, which agrees with f tilde, is uniformly continuous So this is fairly straightforward, that if there is an extension that is continuous, then because that extension is continuous on a closed interval, it is also uniformly continuous, and the uniform continuity of f tilde on AB implies the uniform continuity of f on the open interval AB. Right? I mean, I skipped one step. The fact that f tilde is uniformly continuous on the closed interval AB implies that f tilde is uniformly continuous on the open interval AB. But on the open interval AB, f tilde and f agree. So which means f is also uniformly continuous on the open interval AB. Right? So this part of the proof is actually straightforward. Now let's go the opposite direction. That is, suppose that f is uniformly continuous on AB. We have to argue that an extension is possible to a continuous function on the closed interval. So next, suppose f is uniformly continuous on, let's say, the open interval AB. Now I need to argue that it is possible for me to construct an extension. In other words, we have to define f tilde A and f tilde B, because the extension is identical to f everywhere else, right, on the open interval. It's only at the endpoints that I have to define the extension function, such that f tilde is in fact continuous on the closed interval. Okay, so for the proof, let me just focus on f tilde A. F tilde B is going to be analogously defined. Okay, now what is the intuition here? The intuition for defining f tilde A such that f tilde becomes continuous at A is, of course, that f tilde A should be defined as the limit of f as x tends to a. Okay, so only clearly unless you define it, unless you define f tilde a to be the limit of f as x tends to a, you are not going to get continuity, right? So one has to argue that such a limit in fact exists and uniquely so, right? So the first claim is the following. If say a sequence Sn such that Sn converges to A, then in fact f of Sn also converges. Okay, so if you can construct a sequence in the interval which converges to A, then the claim is that the sequence of function values also converges. All of this is to show that I can define f tilde A uniquely and precisely, right? So this is the first step to proving that. That is that if you find a sequence in the interval AB which converges to A, then in fact the sequence of function values also converges, right? This is not all I need. I also have to argue that two different sequences that converge to A should not result in two different limits when you apply the function values, right? In other words, if you have two sequences, let's say Tn and Sn, right, both of which converge to A, right, then I want to argue that the limit of the function values is in fact the same. Right, so why is that? We'll see. So I have made two claims so far. The first claim is that if you take any sequence in AB which converges to A, then f of Sn converges, and the second claim makes it clear that the limit that you can get of this sequence of function values is uniquely defined. That if you take any two different sequences as well, both of which converge to A, the function values, basically the sequence of function values has the same limit, right? This I claim with these two, I claim that f tilde is f tilde A, I can define it as follows. F tilde A is equal to limit n goes to infinity f of Sn for any such sequence Sn that converges to A, and moreover this f tilde is continuous at A. Okay, so yeah, I leave it to you to convince yourself why that is, right? That is, I haven't proved claim 1 and claim 2 yet, but my subsequent claim is that if these two claims are true, then in fact I can define the extension function at A to be the limit of any of these sequences, right? Sn, Tn, whatever, which converge to A, right? And the extension function defined in this manner is in fact continuous at A. Why is it continuous at A? This is in fact a trivial consequence of the sequential definition of continuity. Alternatively, you should also be able to convince yourself that f tilde has the property that now as x tends to A, the limit of f tilde is in fact equal to this newly defined value of f tilde A. So through either of these, you should be able to easily show that in fact that f tilde defined thus is a continuous function at A. Okay, so now I have to prove these two claims that I've written here, claim 1 and claim 2. So claim 1 is that if you come up with a sequence that converges to A, that f of Sn also converges. So consider some Sn, let's say in the interval AB such that Sn converges to A, right? I have to argue that f of Sn converges to A. This is the proof of claim 1. Yeah. So this is actually fairly straightforward. This follows from the previous result that we proved in this lecture, which is to say that we know that the sequence Sn is Cauchy, because all convergent sequences are Cauchy. And now that I have uniform continuity on the open interval AB, this implies that f of Sn is Cauchy, right? Which again implies that the same sequence converges. Right, so claim 1 is actually fairly straightforward to prove. It follows from the fact that if you have uniform continuity, then if you take any Cauchy sequence within the domain, then the sequence of function values on top of that sequence is also Cauchy. So that's it. That completes claim 1. Now let's go to claim 2. Claim 2 basically tells you that the limit that you get for this fellow is in fact uniquely defined. Right? If I give you two different sequences, Sn and Tn, then f of Sn and f of Tn will have the same limit, right? Which is what tells me that I can unambiguously define f tilde at A. Okay. So to prove this, let's consider two sequences. Let's say Sn converges to A, Tn converges to A. I have to argue that f of Sn and f of Tn, these two sequences have exactly the same limit. Okay, so the way I'm going to do this is the following. Okay, I'm going to first construct a new sequence Zn by interleaving these two sequences. What does interleaving mean? I take one element from the Sn sequence, then I put one element of the Tn sequence, then again I put one element of the Sn sequence, and so on, right? In other words, this Zn sequence could be defined in such a way that all of the odd entries of the Zn sequence are exactly the same as the entries of the Sn sequence in order, and all the even entries of the Zn sequence are exactly the entries of the Tn sequence, again in order. Okay, so I define this new sequence Zn by interleaving Sn and Tn. It is not difficult to see that since Sn and Tn go tend to A, that Zn must also in fact tend to A. Which implies from claim 1 that f of Zn converges. Right? But interestingly, you will see that both f of Sn and f of Tn are in fact subsequences of f of Zn. So the fact that the f of Zn sequence converges implies that every subsequence of this should converge to the same limit. Specifically, f of Sn and f of Tn should also converge to the same limit. Implies that f of Sn, this sequence, and f of Tn, which are subsequences of f of Zn, right, because of the interleaving, also converge to the same limit, right, and that completes the argument. Right? So the moral of the story here is that if you can have uniform continuity of a function on an open interval if and only if it is possible to define a continuous extension of this function over the corresponding closed interval. Right? You should be able to extend the function at the endpoints. Right? Define the function at the endpoints in such a way that that extension function is in fact continuous. Then and only then do you have uniform continuity on the open interval. Okay, so let me give you one example of applying this theorem. So let's define f of x as sin x by x for, let's say, x in the interval 0, 1. Okay, again, unfortunately, yeah, this example is not yeah, it's not very desirable in the sense that I haven't defined any of these functions. I've not defined any of the trigonometric functions yet. So this is jumping ahead, but again, I'm sure everybody has encountered the sine function. So we will, for this purpose of coming up with this illustration, I will pretend for now that you guys are aware of what this function is. Okay, so sine x. Now this function is, again, believe me that sine x is continuous, and since x is not 0 in the interval 0, 1, the ratio of the function sine x and x is also continuous. So this is clearly continuous on the interval 0, 1. Okay, so it turns out that, and I'm sure everybody also understands what is the limit of this function at 0. The limit of this function at x is equal to 0 is in fact 1. So that is in fact, it's possible to come up with this extension. So can define f tilde, let's say extension f tilde of f such that, well, f tilde of 0 is equal to 1, and f tilde 1 is just equal to, well, sine 1, right? And it turns out that f tilde is continuous on 0, 1. Right, the 1 is not really challenging, right? The original function never had any problems at 1 anyway. So continuity of of the extension at 1 is not is trivial. It's actually the continuity of this extension at 0 which requires argument, right? So this is something that we will talk about later, namely that the limit as x tends to 0 of sine x by x is in fact equal to 1. Okay, so this is the part where I need you to believe me that such an extension is in fact possible, that f tilde when defined as 1 at the left end point and sine 1 at the right end point is in fact continuous on the closed interval 0, 1. Now this, from the previous theorem that we just proved, implies that in fact this function sine x by x is uniformly continuous on its domain. Okay, so as such, this was an example of a function which was continuous on the open interval 0, 1. But it turns out we were able to define an extension on either endpoint, right? Because the function actually did have a limit as you approached either endpoint. So that tells you how you can define the extension such that you have continuity of the extension on the corresponding closed interval. And once you have that, by the previous result, you know that in fact your function is uniformly continuous on the open interval 0, 1. Right? So this is just basically telling you that sine x by x is, unlike 1 by x square, is in fact uniformly continuous on the open interval 0, 1. Okay? So that brings us to the close of our discussion on uniform continuity.